Okay. Thank you, everyone, for coming. Good morning. My name is Michaela. These are my partners, Casey and Kyle. We're going to be sharing with you our design of the hybrid petal reactor, a novel photobioreactor design for flue gas conversion to algae. We want to start, I'll go over a bit of the solution that we're trying to address with our hybrid petal reactor. We're going to go into the design process, our profitability analysis, and then finally our recommendations for moving forward. So unfortunately, fossil fuels are expected to be around into the coming decades. We're still going to be heavily reliant on them, so this only further highlights the need for not only emissions reductions and carbon storage programs, but also commercially viable carbon conversion technologies that recognize carbon dioxide not just as a waste product, but as a valuable asset. And that's where we come in. So why did algae? Algae present the fastest and cleanest way to close the carbon cycle on Earth and bring power generation to carbon neutrality, by taking low-density flue gas carbon and converting it into high-density carbon from which we can extract value. So we present to you our solution, the hybrid petal reactor. This reactor intakes flue gas from a coal-fired power plant and converts over 50% of the carbon dioxide present into valuable algae biomass that can then be sold for a wide range of applications such as biofuels, bioplastics, nutraceuticals, and even this candy bar made out of algae. So how does our process work? We intake flue gas at 10% by volume CO2, which is standard for a coal-powered plant. And we take in 200 kilograms of CO2 per day. This is a pilot scale facility. We input that into our algae growth reactor, we downstream process it, and then we sell the biomass for $1.23 per kilogram. We believe that we're on the leading edge of technology at this scale. From a high-profile market assessment of carbon conversion technologies from NRG and COSIA, we believe that only now are the most viable carbon conversion technologies actually breaking into the pilot scale that we're operating at. So that's pretty exciting for us. So how did we actually come up with this? We began with an emphasis on biology. We wanted to make sure that we're harnessing the biosynthetic potential of the algae while maintaining reasonable biological constraints of living systems. So that, combined with an emphasis of practical engineering, we then developed our novel hybrid petal reactor design. From there, we built a reactor simulation using Matlab and Aspen, and then we put it into a profitability optimization in order to get the most viable design specs. So, there it is. This is the overview of the concept of our reactor. So when designing a reactor, you want to focus on, the first step is closed reactor versus open reactor, open to the environment. So we opted to go with a closed reactor setup to maintain our high bioproductivities, even though it's a little more costly than open reactors. Second, we wanted to then know how our light is going to get to the algae. Is it going to be solar light or is it going to be artificial light? We chose to go with solar to reflect our commitment to sustainability, even though artificial lighting offers higher bioproductivities and higher tailorability. But we wanted to maintain all of our carbon conversion goals during the daytime. Next, the next question was how the light was going to actually get into the algae. So we opted for a series of horizontally oriented acrylic tubes that the algae would be flowing through during the daytime. Next, how was the flue gas going to actually get into the algae? Unfortunately, due to mass transfer problems and also due to cost, inline sparging throughout tubes was not going to be viable. Therefore, we chose to add a central gas exchange column. This central gas exchange column would be where the flue gas entered into the column, and the petals, where they got their name from, would extend out from the gas exchange column after receiving a breath of fresh CO2 and then re-enter the column after growth. Finally, we wanted to maintain continuous operation no matter what, even though all our carbon conversion goals are going to be met during the daytime in this tubular gas exchange column setup. So we opted to have a separate tank that has a series of fiber optical lighting cables within it that would then allow for us to have continuous operation not only during nighttime, but during bad weather, during maintenance and repair of your daytime reactor, or during any unexpected circumstances that require you to suddenly boost your population. These fiber optic cables are pretty unique, and they were optimized for profitability as well. They consist of a non-uniform roughening procedure of the core and the cladding. So essentially, when you have an optical fiber cable, you've got light running through it from a source, and it's total internal reflection until you roughen the surface of the cladding in the core, from which light is extracted into the solution. And if you start with a low amount of roughening near the source and end with a high amount of roughening at the end of the tube, then you can achieve uniform distribution of light. So we believe this is the best way to maintain continuous operation no matter what the circumstances were.
All right, so after our biomass has been grown, we need to actually dewater this biomass to make it usable for any kind of value-added product. So this whole process consists of three main parts. This is our downstream harvesting process, and what we're trying to do, like I said, is get that water out of the algae. So the algae cells are all dispersed in this growth medium that we have, and so we need to get them to clump together. We decided to opt for a chemical flocculation process of our algae that consists of raising the pH of the medium and then using magnesium cations to screen the repulsive charges between the cells. That'll get them to flock together, and then we use a dissolved air flotation process to bring these algae to the surface and skim them off. That consists of water that is saturated with air, and we send it through a pressure release valve, causing bubbles to form. The flocks adhere to the bubbles and rise to the top to be skimmed off. Lastly, we have a drying process, and this is really critical because, as I said, we need that algae below a critical moisture content in order for it to be usable. So we've developed a rotary steam tube dryer in which we send the algal paste through the shell side of this heat exchanger while it's rotating to keep the whole process moving. On the other side, running countercurrent will be low pressure steam that will condense over the length of the exchanger. This will be to evaporate the water in that algal paste. Now, this entire process was modeled using an Aspen Plus modeling software program in order to determine that we actually will get the proper amount of heat transfer and make sure that this biomass is at or below our 10% moisture content that we're looking for.
Thank you, Kyle. So as Michaela said, we designed a Matlab simulation for this process to get all the final specifications. So this is just another schematic of the reactor, and I'm going to start, by talking about the gas exchange column. So we modeled gas transfer with the following differential equation, which just describes how CO2 transfers into the bubbles, out of the bubbles into solution, and oxygen transfers the other way. Then we move on to the pedal tube model. So we split the tubes into many differential sections, which is called the plug flow assumption, and we have mass and energy balances across each differential section. So we have balance for algae, which is X for algae concentration, then 2 for the gases, and then an energy balance, which describes how the temperature changes. Now I just need to integrate these across the length of the entire tube. So we have numerical integrals here. The only exception is oxygen, which exits the tube at a saturated concentration. Saturation is reached about a third of the way through the tubes, and then oxygen bubbles are vented after that. So I'm going to discuss the growth rate mu plug in a little bit more detail. So the growth rate varies greatly within each differential section because light attenuates due to absorption of light by the algae. So this figure shows the intensity of light at different portions in a cross-section of the tube. And the light attenuates exponentially, and the growth rate here with I as the intensity needs to be averaged over the cross-section. So with that, we've developed a model for the gas exchange column, which gives the properties of stream 5 as a function of stream 7, and then the pedal tube, which gives the properties of stream 7 as a function of 5, and now we need to put them together. And so we designed an iterative approach where we guess the composition of stream 5, run the pedal tube model, which gives us stream 7, then run the bubbler model, which gives us a new stream 5, and iterate until we get a converged result. So this procedure only has 4 free parameters: the tube length, diameter, cell concentration, and flue gas flow rate. We have to fix the flue gas flow rate to achieve our 50% conversion goal, and now we have these 3 free parameters which we optimize to achieve maximum profitability. So we define an objective function here, which is equal to the negative profits, which we wish to be as negative as possible, as high profits as possible. We use a gradient descent approach, and we arrive at the figures which we've presented previously. We find that we need 13 petals to achieve our total flue gas processing goals. So this is now our final layout of the tubes, given the simulation that we've done. We ran the simulation for this location in northern Brazil, which is an area of a lot of investment in algae technology. And it's a quite compact design. We can fit 2 of them on a standard football field. And we just wanted to do a reality check. So we developed some hypotheses for the specifications before doing the simulation, and we wanted to ensure that they were, our simulation was within the right ballpark, and it indeed was.
All right, so the last thing we did as part of our project was conduct a very rigorous profitability analysis. I'm just going to give you guys the highlights to kind of save on time here, but what's really important is that we ended up with a return on investment of 9%. That's incredible for an algae process like this because really at this point, these processes haven't been profitable before. For our pilot scale facility, our total capital investment was about $75,000, and our annual sales outweigh our annual operating costs by about $8,000, meaning we'll have an opportunity to pay back our initial capital investment over time. In addition, this number is only going to get higher as we continue into the future where lots of work is being done to genetically modify these algae to produce more biomass, to produce more lipids, and that's going to make them more valuable, and we'll be able to sell them at a higher price. And in addition, the climate around these kind of policies is continuing to develop to the point where we might be able to get more opportunities to pay back our investment over longer periods of time with grants from governments and things like that.
Great. So, with the success of our design, both technologically and economically, we have a few recommendations. We believe that the next move would be to build the hybrid pedal reactor. It's a pilot scale reactor, but our simulation is built to be able to be easily scale up. So we believe that our simulation is also tailorable to a wide range of conditions. You can put in any location or species data, and you can run the simulation and obtain your profitable design specs for your plant in a given location. Furthermore, after that, we can obtain empirical data from actually building the reactor. And after that, we can then update and further refine our models in order to reflect biological reality after testing on the pilot scale. After that, it's just a move to scaling up. So we think that this technology has the potential to be pretty disruptive in the carbon conversion and algae industry. And to give you guys a metric for that, if we had 10 facilities operating at 10 times the current capacity, we'd be able to support 10% of the predicted algae biomass market for 2024. And that's pretty exciting, and we're looking forward to the future of algae technology on Earth. With that, we would deeply like to thank the people who've guided us throughout this process. Your support has been invaluable, and we'll open the floor to questions.
So looking at this, it's very much a modeled simulation. Looks great. I noticed you're using magnesium sulfate and sodium hydroxide or lye in the process of separating the algae. Did your design take into account things like how you're going to handle something caustic like sodium hydroxide, and also just the physical dimensions of all this, like where's the night tank, for example, and the diagram showed it under the petals.
Right. So go back to the diagram real quick. Let's see here. So yes, indeed. So yes, the night tank was underground. That also allows us to not have any cooling requirements. It keeps the temperature pretty stable that nighttime. It's just an easy way to drain it underground. So that layout's a pretty simple pedal layout. It's actually much smaller relative to the entire operation.
Talk about addition of chemicals.
Yes, so the addition of chemicals is going to happen upstream of the process. So when we're inputting into the solution into the reactor, the fresh water that's continuously diluting it to provide constant growth rate and constant volume, we're going to be adding in chemicals like NaOH, and we have proper safety mechanisms detailed for those as well as nutrients upstream with turbulent mixing.
So yeah, part of the chemicals will be hand mixed, and then because this is only a pilot scale facility, so we don't really have to worry about that. But then they'll be pumped in continuously.
But the magnesium is added at the end of the process during the flocculation. Yeah.
You talked about profitability and talking that current algae technology is unprofitable. So what makes, I didn't quite understand, what is the advantage of the system over current technologies?
So the advantage of our system is that we have this simulation that gave us essentially, based on biological properties of the algae, the optimal tube size and algae concentration within those tubes to get the most biomass productivity that we can.
It's easily scale upable as well. So each pedal is optimized for the conditions, and it's the number of adding pedals to your overall unit, and then scaling that up as well.
In the financial information, was the $75,000 for the football field program, or was that for
That's right, for half a
That's
football
for
field.
Olympics.
For the
Yes.
yes, for half of a football field size.
Enough to convert 50% of the total flue gas stream of 200 kilograms of CO2 per day.
And that number does seem low. That's because, correct. So that's because really all we're dealing with is plastic equipment and acrylic tubing. All we have to do is these tanks have to be able to hold basically just water. The density of that algal medium is actually very similar to water, so that's why those costs are so low. All right, I think as long as we don't have any more questions, thank you guys very much. We appreciate your time.
Thank you.